Hey everyone, I'm Richard Ledbetter from Digital Foundry. Thank you so much for joining us here for the Rezzed developer sessions. And yeah, thank you for joining us in the auditorium and on the live stream too. Coming up after this session, we have a Media Molecule talking about Dreams on PlayStation 4. But this one, I think, is rather special. So why am I here? Well, when we produce content for Digital Foundry, we're looking for new technology, and typically it's new consoles, new graphics cards, that sort of thing. The idea being to elevate the game experience. But technology evolves in different ways, and I honestly think that the next generation isn't just going to be about what we've got now, but faster. It's going to be about bigger, wider game concepts based on cloud technology. And that leads us onto this, Hadean OS, which is powering a new generation of massively multiplayer experiences. And these guys are here to talk to you about it. So why don't you introduce yourself in turn, and we'll go from there.
So I'm Ryan. I'm the head of PR at Hadean.
I'm Henry. I'm one of the engine developers.
G'day, I'm Mike. I'm the VP of Sales.
Good stuff. So I think we've got a video to show really what you've been up to and to set the scene.
Yeah.
Okay, let's go for it.
Wow! And now they're all hitting me. We're getting the f out of there. That was ridiculous, man.
So that was quite epic, wasn't it? Guys, you've got a bit of a presentation to talk us through what's actually going on here, so take it away.
So I'll just explain, obviously you guys have seen the trailer now, I'll just explain what you're looking at. So this is footage that we captured during our GDC showcase. So at GDC, we had EV Awards, which is the tech demo, and we're quite explicit about the fact it's a tech demo, not a game, because we wanted to show what our Ether Engine technology can do. So as we carry on with this panel, what you'll see in the background, this is actual footage that was captured live during the stress test. You'll see the player counter in the top there is indicating 3,500. We did get to 3,800 real players and 14,000 ships in total. But that's what you're looking at now, essentially, is this is raw gameplay footage that's been captured directly from our GDC showcase. We just thought it'd be a useful reference for you to look at while we talk about the technology that powered it.
Good stuff. So, I mean, this is just sort of absolutely bizarre. But there were, you know, in terms of what we know from gameplay, in a sort of, I guess it's like a death match of sorts, a space death match. I guess the question I've got to ask to begin with is, the aim was to get over 10,000 concurrent players, right?
Yeah,
right.
Yeah. So just to start with, that was the aim. Was we wanted to bring as many players together in a single battle as possible. We knew our technology could do it. Actually, it was more of a logistical challenge, I think, to bring that many players together than we thought. But that was a challenge, yeah. Yeah,
it's a little bit of a partnership story as well, right? Because CCP Games were the incumbents, holding the Guinness World Record with 6,142 players. They're the creators of EVE Online. We've got a long-standing relationship with them. So last year, when we came out to GDC then, the first iteration of the Ether engine, we started having a dialogue with them, and that's evolved into a partnership that's led to this particular demo.
So let's talk about the brass tacks, the basics of how this technology actually works. Because, you know, at the moment, if we look at the sort of the standard big-scale shooters are basically Battle Royale, 100 players, which is, you know, it's not bad, it's impressive, but here we're talking about thousands upon thousands. This is more than just a dedicated server, isn't it? It's basically almost built up from scratch as a brand new distributed computing architecture, right?
Yeah.
Yeah, okay. How does it work? Because obviously, from what I understand, you're scaling up, you're like spinning up servers worldwide as everything is happening in real time, according to the load. Is that right?
So we have our servers that are running in a data center, and there's multiple computers there working together to run the simulation. Then we have, they communicate the data across to other servers that can handle the bandwidth load of sending it out to all of the players.
And I think you touched on it before. Our underlying technology. So just to set the scene, we're not a gaming company. We're not even a simulation company. We're an engineering company that's got a principal focus in distributed computing. So Hadean OS is our underlying technology. That's the technological component that underpins all of this dynamic scaling. The Ether engine is a distributed spatial engine that's built on top of that, a cloud-based engine that does the computational heavy components within a game world like this. And that's tied to the dynamic resourcing. So it can facilitate unbounded worlds, worlds of really intense complexity. In the context of this particular demo, this was a design-driven ambition with CCP Games. So in EVE Online, they've got these massive fleet battles with thousands and thousands of ships engaged in crazy space battles like this. So they were quite interested in pushing the bounds of scalability, but in some of our conversations with other partners, they're much more interested in the kind of fidelity that this dynamic scaling can facilitate. So maybe you've got, you know, 4 players in a small multiplayer map, but they're interested in what if every brick in every building was physically modeled and could dynamically crumble and be destroyed as well.
Right, okay. That's nuts. I guess also there's the question that this was, I mean, you know, let's go back to what we know at the moment of a dedicated server, which is PUBG, for example. You may connect to the Western Europe server. You may connect to the North America server. Your test was a single play area that's global, right?
Yes, that's correct. So we're partnered with Microsoft. And so this demo was built on Microsoft's Azure Edge infrastructure. I think typically when you look at MMO games, they have geographic shards. So if I'm a player in Australia, I connect to the Australian or Oceanic server, et cetera, et cetera. What we were able to do was create this infrastructure using all of these different Azure Edge touch points to create a single uncharted world. Henry, you can probably articulate this a lot better than I can.
Yeah, I guess my question is, there's a reason why current dedicated servers are like that. It's because, you know, it keeps things simple and it keeps latency low. If you've got a global environment, then you must be constantly juggling varying latencies as data travels worldwide, and something somewhere within your algorithm has to decide ground truth, the reality of what is happening in-game, and trying to sift through all of that latency to actually get the best calculation of what is actually happening. How does that work? I just can't comprehend the complexity of this.
So you receive the sort of update of what the view of the world is constantly at 15 times a second. That's sent out to you, and your responses are sent to a local thing, which then communicates to one of our computational simulation engines that tries to work out if what you've sent makes sense with where you currently are and what's going on, and decides what outcome to have happen. So there is a bit of adjustment for if you're, say, behind, it got a high ping, it might adjust what's happened, but that's done in the server, in our tech.
Is there an element, there must be an element of client-side prediction as well to smooth off the...
Yes, so we have some client-side simulation. This was also done as part of our efforts to lower the bandwidth requirements for the client. So, for example, the torpedoes don't only send their position, and it interpolates where the torpedoes are traveling from the positions that you've sent them, and uses that simulation and then updates them as it receives new messages. And similar stuff with the ships. We sort of, if we don't receive an update for a while for a particular ship because they're far away, we would update their position based on our last knowledge of them.
Okay, so this was a stress test, okay? The biggest stress test I can imagine is, what if I'm, in the viewpoint exactly as the footage shows there, and there are 10,000 ships in front of me? Fundamentally, you've got a limitation in bandwidth going from your internet connection to your server infrastructure. How does it cope? How do you manage to balance that load to make it actually playable? Because I was saying to you earlier that this, it's an entirely theoretical situation that could never work, but you've actually seen it. What happened?
So there are two aspects of this. There's the getting the information from our simulation to the player, and for that we use all sorts of fairly common tricks to reduce the bandwidth load. So objects far away are updated less often. If they're too far away, they're not updated at all. Nearby, they're updated much more frequently. We also experimented with things such as hiding objects behind the player and not sending ones that are behind you.
Sure. Yeah.
That had issues where if you span around quickly, it would take a while for it to update, so we ended up not using that.
Sorry, go on.
I was just going to say, and on the client side, there were a lot of tricks to adjust, level of detail and being able to see these things without your game grinding to a halt.
I was just going to mention that. So one of the bottlenecks that we found in this exercise is some of the collaborative software that we've been using. So Unreal Engine 4 was the front end in this particular demo, but it's not designed to render this many entities on screen. So there was a lot of
rather
optimizing.
bravely, you've got a frame rate meter on there, and it is variable. Is that essentially a rendering bottleneck when you get the drops to frame rate there?
Yeah.
And it's not anything to do with the data streaming in from the internet, the positional stuff, that sort of thing. It's purely the rendering thing that's holding things up there.
So it's the data streaming in, the processing that into something to render, and then the render pipeline itself. All of those had bottlenecks along the way, and we've tried to adjust them, and all of those impact the visible frame rate. Mm-hmm. So. Yeah, we're pretty proud to put the frame rate on there and see what people got.
So we've got a combination in here of, I think the peak was like 3,800 real players and the rest was bots. From the server infrastructure side of things, what is the difference between those inputs?
Absolutely none.
None.
So the bots connect using the same method the players connect. They provide the same inputs to the server. They're remote. They're on Amazon Lambdas. They're not hosted on Azure at all. It's completely separate, all communicating in, same bandwidth requirements, same computational requirements within the simulation. There was, as far as simulation is concerned, they're just more players.
But they're not rendering, are they? They're just, or are they?
They're not rendering. No.
Right, okay, fair
But
enough.
they do receive the information back from the simulation, so that's still there, and they update what they're doing based on that information.
So a question I've got about, it happens with just about any kind of multiplayer game, whenever there's a beta test or something like this, we only ever see what's happening on the client side, okay? So we have our own viewpoint. We like to actually do tests where a few of us go into the games and we synchronize the streams and we can kind of see what's going on to get a bit more of a global view of what is happening in, in the server. But what I've always been curious about is, people like you've got basically, you've got I'm presuming you've got like an overview of what was up to 14,000 entities in a single play space. How do you make any sense of that? What data do you get at the end of it? What data do you get in real time? How do you interpret it? Again, this is something where it's something we never see as on the client side, and it's something where I can kind of get an idea when you're doing like a 32, 64, 100-player server. But when you're talking about over 10,000, I can't compute that. I can't mentally envisage it. What did you get to work with there?
So we had, it was in the trailer briefly, an OpenGL client that you could see dots for all the players and all the torpedoes, and that updates at real time centered on the center of the simulation. And that provides a broad overview of where everyone is and what's going on, and generally how chaotic it is. You can see like it's just a cloud of torpedoes. We also had live feedback of how many players were in. We had the player count as a chart that was live updating, and we could see when people were logging in, what our AI count was at, and people logged in like, I think we had almost everyone connected within the first 5 minutes,
right?
Which was quite the challenge.
We didn't know what that uptake would look like, so
Yeah.
while we were at GDC, actually poor Henry was on a live stream on Twitch. We were all kind of trying to suss out how exactly that would play out with the players logging in.
Well, this is an interesting thing. If we go back to the last major beta test for a AAA game, I think it was EA's Anthem, and you couldn't get access to a game because the load was too high. How do you cope with all of these incoming connections? I mean, I think I've seen, based on some of your assets, you've kind of like got a global map, and you can see all of the servers spinning up to accommodate the incoming load. Is that the case?
Yeah, so that was kind of the debug view that Henry touched on earlier. It's in the trailer briefly. For those interested, we'd be happy to show you later after this presentation. But so underpinning the Ether engine, it's built around a distributed data structure called an octree. An octree is basically a way of partitioning three-dimensional space. So if everyone in this room kind of crammed into one corner, the cells in this room would decompose to more granular, to an increasingly granular components. And each of those cells is tied to a computer core. So the more concentrated activity in a spatial region, the more compute resources allocated to it. Conversely, the sparse area of the room, the empty part of the room, would be more coarsely resourced.
Right.
That's the dynamic interplay that Hadean OS provides.
And just to follow on from Mike's point, I think one of the interesting things for us was we did this live at GDC, and a lot of the feedback we heard from publishers and partners was, you're crazy to do this, and they actually highlighted the same problem you spoke to about if you do this sort of tech, and you mentioned one example of a beta test which didn't go so quite well. There are all sorts of unforeseen problems, but we knew and we had enough confidence that we could do this live without running into those sort of issues, and we have done it. So we knew we had a different approach, and that's why we were able to do this live at GDC.
Again, I was looking at some of your PR earlier, and something which I found quite fascinating was that the servers only spool up when they're required. Is that right? So, obviously, if we have a perception of dedicated servers in a current video game, it's that, if nobody's using them, then there's all of these unused computers sitting about doing nothing. But that isn't how this works, right?
Yeah, that's one of the great pain points. If you ask any studio or developer, that's one of the great pain points in multiplayer, right? trying to figure out the provisioning, trying to do capacity planning, load balancing, etc. That's why you see so many launch issues with high-profile games. But this is kind of one of the areas that our technology can potentially mitigate, right? It's providing the resources that you exactly need at a particular moment in time based on the context of the gameplay.
Mm-hmm. So we've got a stress test going on here. The idea of a stress test is to stress it, make things happen that you can't predict. So I guess my question based on that is, what went wrong? if anything. I mean, obviously we're looking at this footage and it all looks, everything's happening as per plan, but what happened?
Well, okay, from my point of view, there were two real challenges we faced. And the first one was, I mentioned this briefly earlier, was the logistical challenge of getting that many players in the same place at the same time.
Right.
We're an engineering company, we're not a gaming company, so for us to kind of take this step into the world of gaming was a learning point for us. And one of the things we learned is it's very, very hard to get a group of very vocal players together in the same game at the same time. And obviously there are a lot of, sounds obvious now saying out loud, but a lot of different time zones and a lot of different players who couldn't make it for X, Y, Z reason. That was, I think, one of the main things that I wouldn't say went wrong for us, but presented an unforeseen challenge for us. So not so much on the technical side, but on the logistical side, certainly that was one of.
So you were looking for 10,000 real players, but you just couldn't logistically amass that amount of people, and your AIs stepped in to make up the numbers. Is that the difference between the red and the orange and the red dots on the HUD? What's that? Or is that missiles and ships?
Missiles and ships.
Right, got you. Uh-huh.
I'll say the mini-map was a lot more functional when we were doing internal smaller tests, and now it's...
yeah, I'm not sure where I am. I assume the player ship is in the center of that.
Yeah.
Okay. One thing I want to talk about at the moment, again, I was reading a lot of the follow-up interviews from GDC, and there's this kind of bizarre perception that you're a cloud-based system, and Google Stadia is a cloud-based system, therefore there's some kind of competition. Now, when I actually went to see Google a week before GDC to check out Stadia, and one of the big things they were talking about is what they call cloud-native apps, which is that basically it's systems designed from the ground up to make use of a massive global network of compute resources. So from my perspective, I'm guessing that it's not actually competitive, but actually extremely complementary, what you're doing, that it could easily transfer across to what Google have as a vision for distributed computing, creating these brand new game experiences. Is that right?
Yeah, that's a great point, Rich. I think we're at an inflection point, right? You're starting to see the emergence of cloud gaming. And a lot of the times we talk about cloud gaming in the context of streaming games, the mythical Netflix of games, but cloud gaming is much broader than that. Generically, it's about taking computationally difficult components of a game and putting them on the cloud. Mm-hmm. From a design perspective, that means you no longer have this, when you're building a game, you no longer have this preconception of this technical ceiling above you, so it's no longer a case of, I can build a game, but it has to fit within this box. I think if you look at the landscape now, it's not just Stadia, you've got Project X Cloud, you've got large studios like EA with Atlas looking at it. You've got non-gaming entities like Verizon playing in this space. A lot of people are interested in the tip of the spear, which is streaming gameplay, ubiquitous gaming on the go on any device. Certainly that's congruent with our technologies. And yeah, when we were in GDC, we spoke to Phil Spencer, and he described the first component of this shift as kind of lazy cloud gaming, and that's kind of like porting existing AAAs onto the cloud.
Right.
But he described, he vocalized the same kind of ambition, right, that you were talking about, Google Stadia, and that's creating cloud-native games. That's games built from the ground up that can fully take advantage of these capabilities.
Yeah, I guess the other thing, of course, is that their kind of pitch is that rather than having a relatively narrow amount of bandwidth between the server and the client, the server and the clients are basically peers on the same network. Does that offer any advantages to what you're doing?
I could definitely see some advantages to that approach in terms of bandwidth requirements, because you'd know what Stadia is requiring, and you would know you would have a good connection between your simulation and the thing that does the rendering. You might be able to do more with that, but it remains to be seen. We haven't investigated.
Okay, good stuff. I guess one sort of final point. Where do you go next? You've done this stress test. Presumably you're happy with the results. CCP seemed to be sort of genuinely blown away. I think, isn't it the case that they are still have legacy architecture that dates back to when CPUs were single core in nature? So this is kind of like, it must be a massive upgrade compared to what they're doing. But obviously you've got a proof of concept here. You've done a worldwide test with thousands of players. What's the next step?
I think in terms of CCP, Hilmar, the CEO of CCP, I think he's been quite vocal about the fact that, they do have some clear technological hurdles they need to address. Now, how they do that, obviously, that's the question for them to answer. In terms of where we go next, I mean, it's a very good question, one we're asking ourselves, right? Because this was a huge, huge milestone for us, not just to kind of in terms of doing this live and successfully achieving what we set out to do, but also, as you touched on earlier, the amount of data for us to pass through, the amount of learnings for us as a company, and also the amount of interest that's been generated off the back of it. I mean, GDC is still fairly fresh, and we're still passing through that. It's a very good question, actually, and it's one we're still answering ourselves.
Yeah, there's a lot of exciting existing work streams that we're doing with our partners, Microsoft, CCP Games, the Francis Crick Institute. We're using the same Ether engine in life sciences to do biomolecular modeling. So there's a lot of stuff in the pipeline already, and there's a lot of exciting conversations that we're having as well.
Yeah, could you talk quickly about the non-gaming applications here? Because this kind of sounds, again, quite staggering and almost beneficial to mankind, almost, of what you're going to be able to open up here.
Yeah, it's kind of interesting. It relates back to how we kind of fell backwards into gaming, because initially when we developed Hadean OS, we built a number of libraries on top of it that weren't based in spatial simulation. We had stuff that was targeting financial services with risk analysis. We had genomic alignment kit. Actually, in the course of talking to some of the players in the life sciences space, they saw the applicability of our technology, and one of our questions to them was, how are you doing this right now? And they're like, well, we use a lot of game engines, we use a lot of game technology. And that's kind of, all of these arrows started pointing towards gaming as an interesting space where we could potentially solve a lot of these computationally interesting problems that we're looking to solve. That's how we kind of migrated into there. But in terms of what we're doing with the Francis Crick, so they're this world-renowned organization. They do a lot of medical research. They're one of the preeminent bodies in cancer research and developing treatments in that space, and we're helping them in that area by using this technology to look at protein-protein interactions. It gets a little bit more scientific than my brain can articulate.
But gaming is actually, a really stressful thing to do, isn't it? It's anything can happen. There's no kind of element of prediction that could account for all scenarios. You've got the human factor going in when you've got so many human inputs going in. So is it kind of like a stress test in that regard as well, in terms of pushing what your technology can do?
Yeah, I think you summarised it quite well. The games industry has a lot of very odd, very specific challenges that, certainly in terms of technology. So we're almost using our foray into gaming as a way to, shape and hone and refine our technology for this broader vision we have at a company, which is, work with the Francis Crick. And certainly the learnings we've taken from gaming will apply in so many other areas. It's just fortunate the games industry does have so many players who are so passionate, who we can call on, who will just, at a moment's notice, come and join our battle and allow us to do things like this, really, because I can't think of many other fields. In fact, I can't think of any other industries where you can do that, really, where you can call upon this sort of stress test in the time we did and at the scale we did.
Good stuff. Well, I'm going to open a questions out to the floor. So if anybody has any questions, please come on up to the stand there, which has now been nicely illuminated. And anything you want to ask, go ahead.
Obviously, your system is dynamically scaling. At peak on this stress test, how many server instances was it using?
Servers total? I'm not sure. Sorry, I was in a separate room at the time. I think it was 5. 5 things, each different CPUs simulating different areas of the simulation.
So what's the total in terms of, scaling that out across thousands of players? Do you know that figure?
No, sorry, I don't
Okay.
know off the top of my head.
And related to that, what was the Azure cost for running this stress test, if you're allowed to say on the no?
That's part of the data we're still passing through, just to touch on
How much it cost? the bill, I guess. Is that what you're asking?
Yes, basically.
Yeah, no, there's part of, for us, as we mentioned earlier, it's part of the data we're passing through, right? Just our GDC learnings and coming through that, because to do something at this scale, as you can imagine, was enormous, right, in every aspect. So, yeah, we're still going through that.
But we're a commercial partner of Microsoft, right? So this is as much an R&D exercise with them as it is with CCP. It's a slightly different commercial relationship than it would be for the average studio developer using Azure for their game, right?
Yep. Well, thank you.
No
Very
worries.
impressive.
Thank you.
I guess, any more questions, actually? No, fair enough. I guess my final question is platforms that could support it. It could be anything, right? Consoles, PCs, cloud systems like Stadia at some point. It's basically, there's no sort of limit on the client side.
Yeah, I mean, philosophically, at a high level, we are very much an agnostic technology platform, right? So we never want to be in that position where we go out to market and work with you guys and say, hey, we've got this great technology, but to use it, you've got to use this cloud, you've got to use this piece of software, you've got to use this front-end engine, right? Mm-hmm. We work collaboratively with all the cloud partners, with all the major engine partners, and similarly, from a client perspective, we're fairly agnostic. Our technology is compatible with mobile gaming just as much as it is with PC or consoles. We try to retain that agnosticity in as much of what we do as possible.
I could be here all day, but I do have one final question, sorry. I guess the other thing we've seen also from the so-called, I think it was back in the day with Microsoft with their Power of the Cloud demo, where they were using distributed compute to do physics. Yes. Is that something? I mean, obviously here the idea is to stress test based on incoming data from thousands of different players, but I'm assuming that your server infrastructure can scale beyond more than just handling player inputs. It could do stuff like physics and stuff like that.
Yeah, definitely. One of the ambitions of Ether Engine is to be able to provide distributed computing capabilities to software that isn't inherently geared for distributed computing. Right. So, for example, existing third-party SDKs, we've got a healthy dialogue with Havoc by way of the Microsoft partnership.
Right.
They've got keen ambitions to explore distributed computing and some of these really gnarly edge cases where you've got complex physics-based interactions that cross servers, stuff like this. And for sure, we've had similar conversations with NVIDIA about physics as well, right?
Good stuff. Well, I guess we're going to wrap it up there. Thank you so much for coming, and thank you for watching if you're on the live stream. And I hope you got as much out of this as I did. It's exciting stuff. And as I said, this is opening the vista to new types of game experience, which personally I find really exciting. So I wish you the best of luck. And next time you're doing a stress test, I'd really like to be in your HQ seeing what you see. That would be great fun. So fingers crossed we can do something like that. But thanks so much for coming. Thanks so much for your time. And thanks for joining us today. Thank you very much.
Thanks, guys.
Thanks.